Hi, it's Ethan again, and today we're going to be talking about specifically the method of polar coordinates. So, to start off, I'll draw an example. You have your frame here, you have your I hat, you have j hat, you have an origin here, you have, this is a fixed frame, but now things get a little bit more complicated. So we're going to add in a rotating frame that is not translating but shares the same origin, and we're going to call this the method of polar coordinates. So right here you have an E hat R, and you have a perpendicular to that, you have an E hat theta. So the difference is really just that this is rotating, and the angle between E hat R and the I hat unit vectors is theta. So for polar coordinates, it's always important to put your point of interest or the center of mass of a rigid body, P, in the E hat R direction. So P is here, like directly in the E hat R direction, because it will help things to cancel out later in your calculations. So to start, I'm going to draw some transformation tables because I think they're helpful and I think they'll help you as well. So for the transformation table, you put what you have to what you want. So you have, you have I hat, j hat, you want E hat R, E hat theta. So what you put in between here is I hat dotted with E hat R, j hat dotted with E hat R, I hat dotted with E hat theta, and j hat dotted with E hat theta. So simple enough. Next I will show what these actually are. So it's the same transformation table but with actual values in it instead. So let's make it really big, I guess. So you have I hat, j hat, and you have E hat R, E hat theta. Then you come back to your diagram and you look at how E hat R and I hat are related. And using trigonometry, you look at it and you say I hat dotted with E hat R is the cosine theta component of E hat R. So you have a cosine theta here. And then in the same way that J is the sine theta component of E hat R, so this is sine theta. Then you look over E hat theta, and the I hat part is negative sine theta, and the j hat component is cosine theta. So these will help you when you're doing problems and doing dot products. You don't have to do them, it's your choice, but I find them helpful, so hopefully they'll help you too. So next I am going to get into the kinematics of it. So some more nice, fun kinematics. So the difference is now you have another additional frame that we're going to call the it's called the R frame that is rotating, and you also still have your fixed frame, but you're going to write it in terms of your rotating frame. So you have R of P with respect to O right here equals, well, I give you a second to think about it. Okay, you had your second, it's a R in the E hat R direction. So it starts off actually easier than the other ones, but gets more complicated for reasons I will go into. So you have r, e hat, r. Okay, so next you want the velocity of p with respect to the fixed frame, and something's different this time. What's different here from the previous video is that e hat r actually is changing with respect to time. So it's going to get a little more complicated. This product rule will no longer you won't be able to just ignore the derivative of e hat, of the I hat, like you did before. Now you actually have to worry about it. So I'm going to show you the easiest way that I think to understand what the derivative of e hat r and e hat theta are. There's other ways you can do it graphically, but I think algebraically makes the most sense to me personally, so that's the way I'm going to show it. So you'll have e hat r down here, alright? E hat r equals, use your transformation table that you have handy right there, cosine theta, alright? I hat plus sine theta j hat. Then take the derivative of this. It's a little easier with respect to time. And you get e hat dot er dot e hat r dot my bad, equals negative, it's a chain rule because the derivative is with respect to time and not theta, so negative theta dot sine theta I hat plus theta dot cosine theta j hat. And you're like, wow, why did he do that? It doesn't seem to be more helpful. But just wait, because it will make sense soon. So now, you look at e hat theta, and you look back at your transformation table, and you say negative sine theta I hat plus cosine theta j hat. And you take the derivative of e hat theta, and you get that e hat theta dot equals negative theta dot cosine theta I hat minus theta dot sine theta j hat. And you're like, things are starting to look familiar, I hope. So you look at e hat r dot, and you're like, wait a second, this is the same as, kind of the same as this, if it was multiplied by a theta dot. So that's how you get the derivative of e hat r dot equals theta dot e hat theta. Then next, you look at e hat theta dot, and you're like, wait a second, this is the same thing as this if it was multiplied by a negative theta dot. So now you have e hat theta dot equals negative theta dot e hat r. So hope that made some sense to you. And I'm going to leave these here, but I'm going to erase these because to make some space. So yeah. All right. So now going back to this, should make a little bit more sense now. We do a product rule here. We get r dot e hat r, all right, plus r. Now we look at our e hat r dot, and we get r times theta dot e hat theta. So that's pretty cool. So next we're going to take another derivative of this with respect to time in order to get the acceleration of p with respect to the fixed frame. So you have a p with respect to the fixed frame equals, let's see what we got here, product rule and another product rule over here. So r double dot e hat r plus r dot theta dot e hat theta. All right. Should have enough room, I think. Take the derivative of this. So this was that. Now we have plus r dot theta dot e hat theta plus r theta double dot e hat theta. And now we're going to have a minus r theta dot squared e hat r. Alright, so now let's group these together in maybe a way that makes a little bit more sense. So you have, put the r's together. These are, you can combine these into one as well, so it makes it a little nicer. You have an r double dot minus an r theta dot squared e hat r plus, so that was this one and that one. Now we're going to do a plus 2 r dot theta dot, which is this and this, and then we have a plus r theta double dot, and this is times e hat theta. So this is the kinematics for the method of polar coordinates where the frame is rotating but it is not translating, and you're using r and theta, no other variables yet. Hopefully that made some sense, and that can help you with problems where your point of interest is in the e hat r, and yeah. So in the next video I will cover rotating frames, but with where the frames actually translate as well, and this will get even more complicated, but it's definitely understandable once you get some practice with it, and yeah, I hope this helps.